This unit focuses on solid, liquid, and gas and how they change from one phase to the next as they interact via intermolecular forces. Now, our focus will be on one of the three different types of intermolecular forces. We have hydrogen bonding, dipole-dipole, and London dispersion forces that all apply in solid and liquid mainly. And that's because in a gas phase, the intermolecular phase is very minimal, whereas solid and liquid, because they're closer in contact with each other, the intermolecular force is much greater and there's a larger amount of it. This video will focus mainly on dipole-dipole intermolecular forces. Now, before I begin, I'd like for you to draw two Lewis structures for HCl and CH3Br. So you will draw HCl here, and right next to it, draw another one. Same for CH3Br. Draw one on the left and one on the right. Come back and check this video. And here is the key. HCl, and these CH3Br, CH3Br. I'm going to draw the dipole-dipole interaction represented in red with a dashed line. So like this. There's an intermolecular between here and intermolecular forces here called the dipole-dipole. So this right here is called dipole-dipole. This is also called dipole-dipole. Okay. So why is there interaction between these two? Why not between hydrogens? Why not between this hydrogen and this hydrogen? And that's because this polar molecule over here has chlorine, and that chlorine has a high electronegativity charge, a high electronegativity in comparison to hydrogen. So therefore, they carry a partially negative charge. The electronegativity basically says, hey, I'm going to take a good chunk amount of my electron in addition to the hydrogen as well. Not fully take on it, but I like to spend more of making sure that electron from the hydrogen comes more towards themselves. Hence why they'll feel this partial negative charge here. Whereas the exposed proton of the nucleus in the hydrogen will be more available on the other end of the spectrum. So therefore, they form this partially positive charge. And this is same for the bromine will have partially negative, and the hydrogens will have partially positive end of the pole. So this entire molecule, we say that this has a dipole moment in that there is a shift where in which they're not neutral, but one side is more negative and the other side is more positive. And it is the attraction between the partially charges of the two different molecules, not same molecule, but two different molecules that creates a dipole-dipole. Now you might say, well, isn't there an attraction between this hydrogen and this chlorine? Yes, there is. There is this partial charges. Of course, they're kind of next to each other, but there's a greater force, is a covalent bond. But I'm not talking about within, but I'm talking about the interaction, the intermolecular forces between one molecule and the next one. So intermolecular forces between this one and this one. So here comes the definition for the dipole-dipole. They're the attraction of partially positive of one polar molecule and partially negative of the other polar molecule. Yes, they have to be polar. In that meaning, polar means that they just have this partial charges and partial negatives. This is not the same as hydrogen bonding because hydrogen bonding involves fluorine, oxygen, and nitrogen that is directly attached to hydrogen. Now, this intermolecular forces out of the hydrogen bonding, dipole-dipole, and London dispersion forces, the three different types of intermolecular forces, the strength of this would be somewhere in between the London dispersion forces and hydrogen bonding. Here's a better way to illustrate it. So I'm going to go a few slides back or just slide back. And here's hydrogen bonding, dipole, dipole, and London dispersion forces. So this hydrogen bonding was the strongest, and then the next strongest would be the dipole, dipole. Hence why I said the strength is of the intermolecular forces, or IMF, would be the medium. Now, how does this relate to the phase changes from solid to liquid to gas? Well, as they go from solid to liquid to gas, okay, they're going to start to break these bonds, these dipole-dipole bonds break as they go through the phase changes. So going from solid to liquid, this is a time where the solid melts into a liquid, and that temperature, we consider that as melting point or melting temperature. That's when it goes from solid to liquid. Some of the intermolecular forces are broken. That's because there's more fluidity, there is movement of the molecules. Going from liquid to gas, there is more breakage of the dipole-dipole, not the covalent bond here, but dipole-dipole as it goes from liquid to gas. And this point, or this temperature in which it does that, we consider that as a boiling point. Note that there is very little or no dipole-dipole interaction here. Let's compare this water, okay, that goes through hydrogen bonding versus that goes through dipole-dipole. That's this one here. So the top one goes through hydrogen bonding. So let me write that. Hydrogen bonding. And then the bottom one goes interacts via dipole-dipole. Okay. So if you look at all of these three, okay, from solid to liquid to gas, solid to liquid to gas, there is a breakage of the intermolecular forces. Just at the top one, you're breaking hydrogen bonding. The bottom one, you're breaking dipole-dipole. So what is the difference, more further difference between the two? Well, water has a higher melting point than HCl. What that means is it takes greater amount of temperature in order from going to solid to liquid than for HCl from going to solid to liquid. More temperature required. What about from going to liquid to gas? Same thing. The boiling point is higher for the water than the HCl. So in general, the molecules with the hydrogen bonding will have a higher boiling and melting point compared to the ones with just dipole-dipole interactions. They're going to have a lower melting point and boiling point comparing the two. So let's do a learning check based on what we have learned so far. Predict which will have the higher boiling point, NH3 or pH3. Explain your reasoning. Come back and try this and come back and check this video. All right, so NH3 will have the higher boiling point. Why? Why does NH3 have the higher boiling point? That's because NH3 can participate in hydrogen bonding. And pH3, though looks much like the NH3, they participate in dipole-dipole. And which one requires more energy to break? Yeah, the hydrogen bonding requires more energy to break. And here we're trying to boil this, going from liquid to gas. So therefore, from going from liquid to gas, the hydrogen bonding, it requires more energy. So they're required for a bigger temperature. So because of their ability to hydrogen bond in comparison to the pH3. So hydrogen bonding, I'll write that down. Hydrogen bonding requires more energy to break the bond compared to dipole-dipole. Thus, greater boiling point.